Imagine stepping into a future where your words can shape the visual world, where every sentence you write is the brushstroke of a masterpiece in motion. This isn't just a dream, it's reality, thanks to OpenAI's groundbreaking innovation, Sora, the video generator that's rewriting the rules of digital creativity. Sora represents a seismic shift in how we create, perceive, and interact with video content. It harnesses the power of transformer architecture, a deep learning model that has revolutionized the field of artificial intelligence to generate videos from textual descriptions. But what sets Sora apart in the vast ocean of AI developments? It's the ability to blend the realistic with the fantastical, to maintain visual quality while adhering to the narrative spun by your words. Whether you're a filmmaker, marketer, educator, or dreamer, Sora offers you a canvas as boundless as your imagination, inviting you to explore, create, and share your vision with the world. The intriguing aspect of these developments is the integration of diffusion and transformer models for video generation. While diffusion provides a method for training models, transformers bring a robust architecture ideal for scaling video generation efforts. The synergy between these approaches, such as in Video GPT, illustrates a conceptually simple yet effective architecture for creating natural videos from textual inputs. This innovative landscape is not just about generating videos, it's about crafting narratives that bridge the gap between human imagination and digital reality, making it possible to visualize anything from textual descriptions. Join us on this thrilling journey into the heart of AI's latest marvel. Discover how Sora is not just generating videos but also possibilities, making the magic of movie making accessible to all. The future of video creation is here, and it's waiting for you to press play. Inspired by the transformative success of large language models, LLMs, which excel by training on vast, internet-scale datasets, OpenAI has embarked on an analogous journey with visual data through the latest innovation, Sora. Just as LLMs leverage tokens to unify a myriad of text modalities, ranging from code and mathematics to a plethora of natural languages, Sora introduces the concept of visual patches, a novel approach to processing visual data. This method is not entirely new. Patches have been recognized as an efficient means of representing visual information in previous research efforts. What sets Sora apart is its application of this technique on an unprecedented scale, enabling the model to learn from and generate a wide variety of videos and images with remarkable fidelity. The process begins with the compression of video data into a lower-dimensional latent space, a crucial step that reduces complexity while preserving essential information. The resulting data is then segmented into space-time patches, which serve as the fundamental building blocks for the model's understanding and generation of visual content. This approach allows Sora to maintain original aspect ratios and resolutions, ensuring that the generated videos and images are not only diverse, but also of high quality. By adopting patch-based representation, akin to the tokenization in LLMs, Sora benefits from a highly scalable and effective framework for training generative models on an extensive array of visual data, marking a significant advancement in the field of generative AI. In the cutting-edge field of video generation, OpenAI's SORA represents a significant breakthrough. The foundation of Sora's capability lies in a specially designed video compression network. This network is engineered to take raw video data as input and transform it into a latent representation that is compressed both temporally and spatially. This compression is crucial for managing the vast amount of information present in video data, making it feasible for Sora to process and generate videos effectively. Once the video data is compressed into this more manageable latent space, Sora is trained to understand and manipulate these representations to generate new video content. The process doesn't stop here. A corresponding decoder model is an integral part of this ecosystem. This decoder takes the generated latent representations and converts them back into pixel space, effectively translating Sora's thoughts into visible, realistic video sequences that we can see and appreciate. This dual process of compression and decoding enables Sora to not only generate videos from text instructions, but to do so with a degree of realism and detail that pushes the boundaries of current generative models. It showcases the potential for AI in creating rich, dynamic visual content from minimal inputs. OpenAI's SORA utilizes a groundbreaking patch-based representation. This methodology involves the extraction of spacetime patches from a compressed input video, treating these patches akin to transformer tokens. This conceptual framework is equally applicable to images considered as videos consisting of a single frame, allowing for a unified processing mechanism for both media types. The essence of this approach lies in its versatility and adaptability. By leveraging patch-based representation, Sora is adept at handling visual data across a wide spectrum of resolutions, durations, and aspect ratios. This flexibility is foundational to Sora's training process, enabling it to learn from and adapt to a diverse set of visual inputs. During the inference phase, the model's capability to generate videos of varying sizes is showcased through the strategic arrangement of randomly initialized patches within a grid of appropriate dimensions. This innovative strategy not only ensures the generation of high-quality content tailored to specific requirements, but also illustrates the model's robustness in creating visually coherent outputs from a vast array of inputs. Sora, a cutting-edge fusion of diffusion model techniques with transformer architecture, known as a diffusion transformer. This innovative approach leverages noisy patches along with conditioning information, such as text prompts, to train the model to reconstruct the original, clean versions of these patches. The significance of Sora being a diffusion transformer cannot be overstated. Transformers, since their inception, have shown exceptional ability to scale across diverse domains, ranging from language modeling to computer vision and now, with Sora, extending into video model generation. The core principle behind Sora's functionality is its capacity to improve the quality of video samples as it undergoes more training iterations, supported by increased computational resources. This scaling efficiency is particularly notable in the domain of video generation, where Sora demonstrates a remarkable ability to produce high-quality video content from textual descriptions. As training progresses, with fixed seeds and inputs, the quality of the video samples generated by Sora enhances significantly. This progress underscores the model's potential in transforming the landscape of video generation, making it a pivotal tool in the creation of dynamic, realistic video content from minimal input data. The evolution of image and video generation techniques has taken a significant leap forward with OpenAI's Sora, moving away from the traditional practice of resizing, cropping, or trimming videos to a uniform size. By opting to train on data in its native size, Sora unlocks a plethora of benefits, enhancing the model's versatility and output quality. Sampling flexibility. Sora's ability to sample videos in a wide range of resolutions, from widescreen 1920x1080 to vertical 1080x1920 and everything in between, marks a departure from the constraints of past models. This flexibility allows for the creation of content optimized for various devices directly in their native aspect ratios. Furthermore, it enables rapid prototyping at lower resolutions, facilitating a seamless transition to full-resolution outputs without the need to switch models. Improved framing and composition. Training on videos in their original aspect ratios has empirically shown to improve both the composition and framing of the generated content. Traditional models, which often resort to cropping videos to square formats, can result in compositions where subjects are partially cut off, or not ideally positioned. In contrast, Sora, by preserving the original aspect ratios, significantly enhances the framing, ensuring that subjects are fully visible and well placed within the scene. This advancement underscores the importance of native-size training in achieving more natural and appealing visual outputs. The development of text-to-video generation systems, such as OpenAI's Sora, has advanced significantly through innovative approaches to language understanding. A pivotal technique employed in this process is the recaptioning method, initially introduced with DALL-E 3, now adapted for video content. This method involves training a highly descriptive captioner model on a vast dataset of videos, each paired with corresponding text captions. The captioner model is designed to generate detailed text captions for all videos in the training set, enhancing the system's ability to understand and interpret the content accurately. The impact of training on these enriched, highly descriptive video captions is twofold. First, it significantly improves text fidelity, ensuring that generated video content closely aligns with the textual descriptions provided by users. Secondly, it elevates the overall quality of the generated videos, making them more coherent, visually appealing, and contextually accurate. Building on the foundation laid by DALL-E 3, the Sora model incorporates GPT's capabilities to transform short user prompts into longer, more detailed captions. These enhanced captions are then fed into the video generation model, allowing Sora to produce high-quality videos that faithfully adhere to user prompts. This synergy between advanced language models and video generation technology marks a significant leap forward in creating dynamic, responsive, and user-driven video content. OpenAI's Sora transcends traditional text-to-video capabilities by accepting a broader spectrum of inputs, including pre-existing images or videos. This versatility opens up a realm of possibilities in image and video editing tasks. Sora's ability to animate static images, such as those generated by DALL-E 2 and DALL-E 3, exemplifies its capacity to breathe life into still visuals, transforming them into dynamic videos with the aid of a simple prompt. Moreover, Sora's proficiency extends to video manipulation, allowing it to extend the duration of videos either forwards or backwards in time. This unique feature enables the creation of content that is not just extended, but can also loop seamlessly, enhancing the visual storytelling experience. Through the use of segments from generated videos, Sora demonstrates its capability to produce multiple videos that, despite starting differently, converge to the same endpoint. This methodological approach not only showcases Sora's advanced editing functionalities but also highlights its potential to generate content that is cohesive and continuous, opening new avenues for creative expression and digital content creation. The integration of diffusion models into video editing, particularly through OpenAI's Sora, has significantly broadened the scope of creative possibilities. One notable method employed is SDedit, which allows Sora to effortlessly transform the styles and environments of input videos in a zero-shot manner. This means Sora can make these transformations without needing any additional training specific to the new style or environment, directly applying changes based on the text prompts provided. Moreover, Sora's capability extends to connecting videos by gradually interpolating between two distinct input videos. This feature facilitates the creation of seamless transitions between videos that may vary greatly in terms of subject matter and scene composition. Through this technique, Sora generates a series of intermediate frames that naturally bridge the gap between the two videos, making it appear as though the content is smoothly evolving from one scene to the next. This innovative approach to video editing opens up new avenues for storytelling and content creation, allowing creators to blend disparate videos into a cohesive narrative or visual experience effortlessly. OpenAI's Sora extends its capabilities beyond video generation to include the creation of static images. This is accomplished by leveraging a unique approach that involves arranging patches of Gaussian noise within a spatial grid that spans a temporal extent of just one frame. Through this innovative technique, Sora is equipped to generate images of varying sizes, with the capacity to reach resolutions as high as 2048 x 2048. This feature not only showcases Sora's versatility in handling both video and image content, but also highlights its potential to produce high-resolution images suitable for a wide range of applications, from digital art to content creation. The ability to generate such detailed images from Gaussian noise patches demonstrates the advanced technological underpinnings of Sora and its potential to revolutionize the field of generative AI. OpenAI's Sora showcases remarkable emergent capabilities in simulating real and digital worlds, attributed to its training on a vast scale. These features emerge naturally, without any pre-programmed biases towards 3D modeling or object recognition, underscoring the model's ability to learn complex representations from data alone. 3D consistency. Sora demonstrates the ability to produce videos with dynamic camera movements, maintaining a consistent representation of people and objects in three-dimensional space. This capability ensures that as the perspective changes, the spatial relations and movements within the scene remain logical and fluid. Long-range coherence and object permanence. One of the long-standing challenges in video generation has been achieving temporal consistency over extended periods. Sora exhibits proficiency in this area, often successfully modeling both short-term and long-term dependencies within a video. It can maintain the continuity of characters, objects, and animals across various scenes, even in cases of occlusion or when they temporarily exit the frame. Interacting with the world. Sora can simulate simple interactions within its generated environments. Examples include a painter adding strokes to a canvas over time or a character consuming food, leaving behind realistic changes in the scene like bite marks. Simulating digital worlds. Beyond physical simulations, Sora adeptly replicates digital environments such as video games. It can control a character in a game like Minecraft, rendering both the character's actions and the game's dynamic world with remarkable fidelity. This capability is particularly impressive as it can be prompted to simulate specific scenarios like Minecraft gameplay without direct training on those tasks. These emerging capabilities indicate that further development and scaling of video generation models like Sora could lead to the creation of advanced simulators. Such simulators would not only replicate aspects of the physical and digital worlds, but also the complex interactions of entities within these environments. OpenAI's Sora, while groundbreaking in its ability to generate videos from text prompts, is not without its limitations as a simulator. Currently, Sora struggles with accurately modeling the physics of basic interactions, such as glass shattering and other scenarios like the consumption of food may not result in the correct changes to object states. Additionally, the model is prone to common failure modes including incoherencies in longer duration samples and the spontaneous appearance of objects, which detract from the realism and coherence of the generated content. Despite these challenges, the capabilities that Sora demonstrates today are significant. They suggest that with further development and scaling, video models like Sora could become highly capable simulators of both the physical and digital worlds. The vision is to develop a system that can accurately simulate the complex interactions and dynamics of objects, animals, and people within these environments. The ongoing efforts to refine Sora and address its current limitations are seen as crucial steps on the path toward achieving this goal. The potential of such technology to revolutionize video generation, content creation, and even simulation-based learning and research is immense, marking an exciting direction for future advancements in generative AI.